Hello everyone, this is Surendra Babu and the title of my presentation is Simplified Cluster Balance Control of Cascaded H-bridge STATCOM under Unbalanced Grid. The outline of my presentation is as follows: Introduction, Motivation, Proposed Cluster Balance Control, Simulation Study Results and Conclusions. STATCOM plays an important role in a power system network with increased power generation from renewable energy resources. Stable operation of STATCOM is essential under unbalanced grid, including LVRT with good dynamic response. Cascaded H-bridge multi-level STATCOM is best suited for medium and high power applications. The merits of the topology are modularity, scalability, and good harmonic profile. The main limitation of the topology is floating neutral, requiring additional control to balance power among the three-phase clusters. The overall control of cascaded H-bridge multilevel STATCOM is divided into three parts. First one, total DC voltage control of three-phase clusters and reactive current control. Second, DC voltage control of the phase clusters known as cluster balance control. Third, DC voltage control of H-bridge inverters of the phase clusters, also known as individual DC voltage control. Under unbalanced grid, the negative sequence components of the grid voltages interact with the positive sequence current components of the multilevel STATCOM. Under such conditions, the average power in each phase has two components, balanced and unbalanced. The unbalanced power components lead to unequal DC voltages among the phase clusters. When the cluster balance controller of the multilevel STATCOM tries to equalize the DC voltages, the multilevel STATCOM starts drawing a negative sequence current. The three-phase grid voltages under unbalanced grid is given using equation 1, and the STATCOM currents when there is cluster balance controller are given in equation 2. The instantaneous power in each phase can be obtained by multiplying voltage with respect to current. The average power components in each phase are obtained by selecting the product terms which result in average power. The balanced power per phase can be given using equation 4, and unbalanced powers of phases A, B and C can be given using equation 5. When there are negative sequence components in the voltages and currents, deriving expressions of average power is a difficult task and requires a lot of meticulousness while deriving and implementing the algorithm. Most of the latest schemes are based on the information of unbalanced power in the phase clusters with complex control algorithms requiring large derivations and a lot of supporting analysis. There are three types of cluster balance control schemes: zero sequence voltage control, negative sequence current control, and the combination of zero sequence voltage and negative sequence current control. Motivation: with the zero sequence voltage control, the degree of freedom is limited. Therefore, this control draws excessive negative sequence current, necessitating to increase DC voltage to avoid overmodulation. Further, deriving expressions for magnitude and phase angle of zero sequence voltage is a laborious task, and final expressions are complicated. The negative sequence current control schemes also require large derivations and a lot of calculations and could not yield desired result, drawing excessive negative sequence current. Therefore, schemes were reported combining the zero sequence voltage and negative sequence current, complicating the control algorithm further. Moreover, the schemes that are reported cannot realize complete DC voltage balance. There exists some steady state error in the DC voltages of three-phase clusters. Hence, to avoid unstable operation, individual DC voltage control is reported using a proportional controller, which results in unequal DC voltage across the H-bridge inverters. The following part of the presentation consists three components: total DC voltage and reactive current control, proposed cluster balance control, and individual DC voltage control of H-bridge inverters. The positive sequence DQ components of the multilevel STATCOM are controlled using equations 6 and 7. The control parameter X1 controls IDP using PI controller as shown in equation 8. IDP controls the total DC voltage of three-phase clusters using PI3. The control parameter X2 controls reactive current component according to the requirement. The total DC voltage and reactive current control is shown in figure 2. The PI controllers PI1 and PI3 ensure that the total DC voltage of three-phase clusters is maintained at the reference voltage, including when grid voltages are unbalanced. When there is a dip in the grid voltages, the total DC voltage is maintained at the reference by drawing more IDP. Therefore, as the total DC voltage of three-phase clusters remains constant, it is sufficient to control DC voltages of any two clusters to realize equal DC voltage balance among the phase clusters. The negative sequence DQ voltage components of the multi-level STATCOM can be controlled similar to the positive sequence components and are given in the equations 12 and 13. The control parameter X3 is derived to control IDN and IDN is derived to control the total DC voltage of a phase cluster using PI controllers PI4 and PI6. The control parameter X4 is derived to control IQN and IQN is derived to control the DC voltage of B phase cluster using PI controllers PI5 and PI7. The proposed cluster balance control is shown in figure 3. The PI controllers PI4 and PI6 ensure that the DC voltage of A phase cluster is maintained at the reference voltage. The PI controllers PI5 and PI7 ensure that the DC voltage of B phase cluster is maintained at the reference voltage. The DC voltage of A phase cluster is directly controlled by IDN and that of B phase by IQN. The DC voltage of C phase cluster is indirectly controlled by IDP. The DC voltages of three-phase clusters are independently controlled, resulting in a fast dynamic response. The proposed cluster balance controller realizes zero steady-state error in the DC voltages of three-phase clusters. This makes it possible to use PI controller for the individual DC voltage control. The individual DC voltage control, which was already reported by the same author, is applied in this work. The positive sequence Q components of the H-bridge inverters is controlled to control the DC voltage of H-bridge inverters as given in equation 19. The individual DC voltage control is shown in figure 4. The positive and negative sequence DQ components are inverse transformed to stationary ABC frame and gate signals are generated using phase shifted sinusoidal PWM. The effectiveness of the proposed scheme is verified with simulation studies in MATLAB Simulink on a 9-level 11 kV 2 MVA STATCOM, and the simulation system parameters are given in table 1. The controller is implemented in per unit and all the required quantities are either measured in per unit or converted to per unit. Case 1. Balanced grid voltages. At t equals to 2.5 seconds, the reference reactive current I star QP is changed from +1 per unit to -1 per unit. Figure 5b shows the response of STATCOM reactive current. And figure 5a shows the response of DC voltages of three-phase clusters. Figure 5c shows line-to-line voltage of the multi-level STATCOM in capacitive mode of operation. Case 2. Voltage dip of 50% in A phase from t equals to 2.5 seconds while I star QP is set at +1 per unit. In this case, the grid voltages are balanced at t equals to 2.5 seconds. At t equals to 2.5 seconds, the voltage of A phase falls to 0.5 per unit as shown in figure 6a. The DC voltage of A phase cluster is shown in figure 6b and the DC voltage of B phase cluster is shown in figure 6c. The response of negative sequence current components is shown in figure 6D. In the steady state, from the simulation study, it is observed that IDN equals to minus 0.01 per unit and IQN equals to 0.195 per unit. Case 3, voltage dip of 50% in the A and B phases. In this case, the grid voltages are balanced till t equals to 2.5 seconds. From t equals to 2.5 seconds, the voltages of A and B phases fall to 0.5 per unit as shown in figure 7a. Figure 7b shows the DC voltages of A phase H-bridge inverters, and figure 7c shows the DC voltages of B phase H-bridge inverters. Figure 7d shows the response of negative sequence current components. In the steady state, it is observed that IDN equals to 0.21 per unit, and IQN equals to 0.13 per unit. Conclusions. The cluster balance schemes that are reported using either zero sequence voltage or negative sequence current or combination of both are complex and laborious. A simple cluster balance scheme is presented using a negative sequence current control without requiring any additional calculations. The magnitude of negative sequence current drawn from the grid is in reasonable limit. For a voltage dip of 50% in one phase, the magnitude of negative sequence current is 19.53%, and for a voltage dip of 50% in two phases, it is 24.57%. The DC voltages of three-phase clusters are independently controlled, resulting in fast dynamic response. The scheme realizes zero steady-state error in the DC voltages of three-phase clusters, which makes it feasible to realize equal DC voltage among three-phase H-bridge inverters. The scheme is generalized and can be extended for other applications of the topology. These are the references that are mainly followed for this work. I thank you all for your attention.